I want to go through this one last example in a little bit of detail here because it's going to end up being important later on. And so we're going to consider the relation modulo 3 on the set 0, 1, 2, 3, 4, 5, 6. And so by that I mean that any two things are related to each other as long as they're equal mod 3. From a mathematical perspective, mod n is really defined as a relation and not as an operation. And so we'll see what that means here. And so first I want to write out the set representing this relation. And so that just means that I need to write out, again, the laundry list of ordered pairs of all possible things that are related. And so it'll be helpful to stay organized by trying to write things in relevant clumps. And so what I mean by that is that, of course, we know that 0 and 3 and 6 all are the same mod 3. We also would know that 1 and 4 and 2 and 5 are the same mod 3. And so I might as well write out all the possible relations for each of these three clumps individually. And so if I do that, first, I can see that I would have 0, 0, 0, 3, 0, 6, and then 3, 0, 3, 3, 3, 6, and then 6, 0, 6, 3, and 6, 6. And so that's corresponding to that first clump of 0, 3, 6. And here you can see that you have every possible combination of a 0 in the first entry, a 3 in the first entry, a 6 in the first entry, and the same for the second. And so you could tell then that overall there's going to be 3 times 3 ordered pairs, or 9, corresponding to these three numbers. I could do the same thing then with 1 and 4. And so I'll have 1, 1, 1, 4, 4, 1, and 4, 4. And again, I can tell that I should have had 4 ordered pairs total here because there's 2 choices for the first and 2 choices for the second. And then of course the 2 and the 5 are the same sort of deal. So I'm going to get 2, 2, 2, 5, 5, 2, and 5, 5. Okay, so first let's talk about the properties: reflexive, symmetric, transitive, and antisymmetric. And so here you can tell that this is going to be reflexive, because k mod n is always equal to k mod n. And so that looks a little trivial when I write it that way, but in other words, the remainder when you divide by n is always going to give you the same thing if you're starting with the same number. All right, the next thing is symmetric, which I spelled wrong. There we go. And so here you could tell that this will be symmetric because if k is equal to L mod n, then it is still the case that L is equal to k mod n. Right? So if I take the remainder of both of them when I divide by n, then it doesn't matter which order I do it, they're still going to be equal. If we look for transitivity, this is also true in this case, because if k is equal to L mod n, and also L is equal to m mod n, then it is the case that k is equal to m mod n. By the way, here I sort of switched to writing mod n, but it's really the same as mod 3 in this case. And so this is just showing that you could do everything more generally. And so the last thing is antisymmetric. And this is not true here, because 0 is equal to 3 mod 3, and 3 is equal to 0 mod 3, right? Because they both have the same remainder when you divide by 3, but 0 is not literally equal to 3. And so that means that this cannot be antisymmetric. It would also be helpful to draw this as a graph, as we've done for the other ones. And so the way I'm going to draw it is by having numbers that are related to each other close to each other. And so I would have this 0, 3, and 6. And then I'd also have 2 and 5, and also 1 and 4. All right, in each one of these clumps, everything is going to be related to each other. So first of all, everything is related to itself. And then I'm going to draw every possible arrow between two elements inside each clump. Okay, so first of all, in a graph theoretic phrasing, each one of these objects right here, the 0, 3, 6, the 2, 5, and the 1, 4, would be referred to as a clique, or sometimes clique, and that just means that every possible connection is there. Another thing is that this is very characteristic of what is called an equivalence relation, which you'll see more about later on this worksheet. And the idea is that any time that a relation is reflexive, symmetric, and transitive, like this one, then it's always going to divide up your underlying set, which in this case is 0, 1, 2, 3, 4, 5, 6, into these clumps. And so if I view it as a graph, that means it's going to divide it into cliques, where among every group, all the connections are present, and then between groups, no connections are present. And in terms of the laundry list of ordered pairs, that means that we can have these three different bands in this case, or they could be any number of bands in a different case, where on each line here, every possible relation between the numbers is present, but then between lines, no relations are present. So in other words, every possible relation between 0, 3, and 6 is somewhere on this top line. But between the lines, there are no relations, for example, between 0 and 1, because those occur on different lines. And so that's a really important structure for these sorts of relations, and it's something that we'll see consistently whenever you have something that's reflexive, symmetric, and transitive.